Hello students, I hope all of you are doing good. In last class we were discussing about periodic classification. Today we will go for the another chapter, that is chemical bonding. So revision of chemical bonding. Chemical bonding. Again, this is very important chapter, chemical bonding and periodic classification. So please go through that, your proper notes. Alright, while revising the chapter, you should keep your notes in front of you and then you see all the details. So in chemical bonding, we will discuss about, we will revise the things in two different parts. We will discuss about ionic bond, then polarization, okay. Then after variation of melting and boiling point, variation of solubility, we'll go for that, variation of solubility. Then we'll discuss covalent bond, dipole moment, okay, dipole moment, little idea about resonance, then we'll go for valence cell electron pair repulsion theory, we'll go for bond parameters, okay, then we'll go for hybridization, then we'll discuss about molecular orbital theory, hybridization and hydrogen bonding, we'll go for that. So this is a part of chemical bonding. So let us start from ionic bond itself. Okay. So the very first theory was electronic theory of valency, which was proposed by Lewis and Cossel. Electronic theory of valency, which was proposed by Lewis and Cossel. And according to this, every element will have tendency to form, alright, ionic bond, covalent bond or coordinate bond, basically three types of bond. Every element will have tendency to acquire electronic configuration of inert gas element, and for this they either undergo loss or gain of electron, or share their electron, or donate a pair of electrons. By this way they forms ionic bond, then covalent bond, and then after coordinate bond. Coordinate bond is also known as dative bond. This is also known as dative bond. Okay, so ionic bond is what? The bond which is formed by the transfer of electron. That is, transfer of electron takes place in between metal and non-metal, whose electronegative difference is greater than 1.7. So if there is Na, there is one electron, chlorine requires one more electron, so this electron is being lost by them, chlorine will gain electron, this will become Na plus, this will become Cl minus, and there will be combination between Na plus and Cl minus to give NaCl solid crystals. That is the formation of ionic bond. Ionic bond is purely electrostatic in nature. Alright, and therefore this ionic bond is strongest bond among covalent and coordinate. Among all chemical bond, ionic bond is strongest bond, isn't it? So ionic bond is strongest bond. Conditions for the formation of ionic bond is that metal should possess or must possess low value of low ionization enthalpy. Low ionization enthalpy will favor the formation of ionic bond. Then non-metal must possess high value of electron gain enthalpy. Electron gain enthalpy should be large negative to form ionic bond. And then lattice energy or lattice enthalpy should be very high. So lattice enthalpy, alright, must be very high, very high. So lattice enthalpy must be very high for the formation of ionic bond. So metal must possess low ionization energy, non-metal must possess high electron gain enthalpy, and lattice enthalpy must be very high for the formation of ionic bond. These three are or we can say these three are the major conditions for the formation of ionic bond. Okay, so like suppose there is NaCl we need to form. NaCl for the formation of solid crystal lattice structure, what we need to do, we must have Na plus, alright, Na plus gaseous and Cl minus gaseous ion. Na plus gaseous ion must be produced from Na gaseous atom. Cl minus gaseous ion must be produced from Cl gaseous atom. Na gaseous atom is produced from Na solid, and so chlorine gaseous atom is produced from chlorine molecule, which is gaseous molecule. So by using dissociation enthalpy, and then Na plus half Cl2 will form NaCl crystal. So for the formation of this, alright, ionic bond, there are two different processes, two different ways, two different theories, alright, were explained the formation of ionic bond. One was Born-Haber cycle, other was Born-Land equation. So Born-Haber cycle states that, alright, ionic bond must be formed by a cycle covering a cycle itself. Alright, that cycle is called as Born-Haber cycle. If you see in this case, this NaCl is formed from their constituent element Na and Cl2 gaseous, and whatever the energy released or absorbed will be there, that is their enthalpy of formation of sodium chloride. Then this Na solid is converted to Na gaseous by giving enthalpy of sublimation. So that solid atom is converted to gaseous atom. Then again half Cl2 chlorine gas molecules are there. We need to break their bond by using their bond dissociation enthalpy. So half of delta H of bond dissociation enthalpy will break their covalent bond and convert them into chlorine gaseous atom. Na gaseous, by using enthalpy of ionization, they will undergo loss of electron, becoming Na plus gaseous, and by accepting electron, they will have electron gain enthalpy. Electron gain enthalpy will be negative, ionization enthalpy will be positive, enthalpy of sublimation will be positive, and enthalpy of bond dissociation will be positive. When these two will combine together, they release a certain amount of energy, which is called as lattice enthalpy, and that must be negative. For the formation, for breaking, that must be positive. So lattice enthalpy can be calculated as the amount of energy released when 1 mole of gaseous cation combines with 1 mole of gaseous anion to form corresponding solid crystal lattice structure is called as their lattice enthalpy, or the amount of energy net amount of energy which is absorbed when 1 mole of solid crystal lattice structure is broken down into corresponding gaseous ions. The amount of energy absorbed is called as their lattice enthalpy. Alright, and this cycle is called as Born-Haber cycle. So according to Born-Haber cycle, ionic bond must be formed by covering a cycle itself, okay, which consisting of all sort of energy. If you see this, so enthalpy of formation of a compound, ionic compound, is equals to, over here we can say enthalpy of sublimation plus enthalpy of half of enthalpy of bond dissociation plus ionization enthalpy minus electron gain enthalpy minus lattice enthalpy. Alright, lattice enthalpy. So enthalpy of formation of any ionic compound is written like in this energy format. So lattice enthalpy, this is over here enthalpy of formation of sodium chloride. This enthalpy of formation must be the summation of all these enthalpies. So enthalpy of this plus enthalpy of this plus enthalpy of this plus enthalpy of this plus enthalpy of this will give you the enthalpy of formation of that particular ionic compound. So ionic compound, to form ionic compound, metal must possess low value of ionization enthalpy because it is energy required, and must releases high value of energy, which is their electron affinity or electron gain enthalpy. So large negative value of electron gain enthalpy will favor the formation of Cl minus or will favor the formation of anion. Low value of ionization enthalpy will favor the formation of cation, and when these two will combine together to form the solid crystal, the energy released will be called as their enthalpy of lattice. So this Born-Haber calculation will involve this one. Another is that is Born-Land equation. According to Born-Land equation, what we can say, we can show the variation Born-Land equation. Born-Land equation, according to which that is lattice enthalpy is equals to summation of attraction energy plus summation of repulsion energy. Attraction energy is written as negative, that is Z plus Z minus A Na by R square. So what is this? Minus Z plus Z minus A N0 by R square plus this is what? B upon R to the power N. This is the value of their lattice enthalpy. Since net value is attraction, even there is attraction as well as repulsion, but net is attraction. Therefore, the net value, net energy value must be negative. Where Z plus Z minus is charge on cation and anion, R is ionic distance or radius, ionic radius, A is a constant which is known as Madelung constant, B is a constant which is repulsion coefficient, N is Born exponent. Okay, all this. So from this relation, what we use, the U is proportional to Z plus and Z minus, while inversely proportional to radius. That is, U is proportional to Z plus and Z minus and inversely proportional to radius, isn't it? So by using this Z plus and Z minus, we can find out which will have high value of lattice enthalpy, which will have low value of lattice enthalpy. Okay. We can compare the lattice enthalpy value for any two compounds. Okay. Lattice enthalpy plays very important role. Lattice enthalpy plays very important role while giving the variations of melting and boiling point and solubility of ionic compounds. Usually what we can say, U greater than U, as the U increases, okay, U increases, if U is more, melting point and boiling point of solid is more. U is more, melting point and boiling point of ionic crystal is more. U is more, stability of ionic crystal is more. Stability of ionic crystal is more. So stability of ionic crystal is more if U is more. So melting and boiling point is proportional to U. Stability of ionic crystal is proportional to U. Okay. Now, this variation of U, alright, variation of U depends upon radius as well as Z plus and Z minus. Suppose we have Na2O, we have MgO, we have Al2O3. If you see this, Na2O, Z plus and Z minus, the value of Z plus and Z minus, the product of this will be Na plus and 2 minus, 1 into 2. This is what? 2 into 2. This is what? 3 into 2. So over here 2, over here 4, over here 6. Where is Z plus Z minus is more? In Al2O3. Therefore, Al2O3 will have higher value of melting and boiling point than MgO, than Na2O. So this is the value of their lattice enthalpy as well as melting point and boiling point according to lattice enthalpy. Okay, and we have explained this lattice enthalpy and melting and boiling point variations in details. So again, please go through the notes itself. Okay, that was about lattice enthalpy variations. Similarly, lattice enthalpy varies as radius of cation plus radius of anion. Radius of cation plus radius of anion. Is there ionic distance? So radius of cation plus radius of anion that is U varies the ionic distance, okay, by radius of cation. Suppose cation is same for all, anion is different, then greater the radius of anion, lower will be the value of their lattice enthalpy. Like this, we can show the variation of their lattice enthalpy. Okay. Now, in their ionic compounds, in their properties, we have seen properties of ionic compounds, that is they possess very high value of melting and boiling point. Their ionic bond is polar in nature. Ionic bond is what? Ionic bond is having charge, that is complete electrostatic force of attraction between cation and anion. That compound must be completely polarized, completely ionized. Ionic bond is non-directional because it is the concept of loss or gain of electron, so it should not have any directions. Ionic bond is non-directional in nature. Ionic compound molecules are soluble in water or in polar protic solvent, because we know that like dissolves like. So polar molecule is soluble in polar solvent, non-polar molecule is soluble in non-polar solvent. Okay, some of the ionic compound which are insoluble in water but soluble in organic solvent, their solubility can be explained by using polarization. That is, higher the value of polarization, lower will be their solubility. Polarization stands for their covalent character. So then we will discuss about polarization. Polarization is what? Polarization. Suppose there is cation, cation is smaller in size, anion is bigger in size. So when cation is smaller in size, if there is smaller in size, obviously at the surface of this cation, residual nuclear force is very large. At the surface of anion, residual nuclear force is very less, very small. So what we can say, if residual force is very large, so they will have large force of attraction, they will have tendency to attract the electron cloud towards themselves. So cation possesses polarizing power. Cation possesses polarizing power. Anion is having tendency to get polarized, that is, they are having polarizability. Ability to polarize, that is polarizability. So when cation comes closer to anion, cation will attract the outermost electron cloud of anion, due to which what will happen? Their structure gets distorted, and finally cation and anion lies on the same region. So finally, cation and anion lies on the same region. Cation and anion lies on the same region. This is the thing where cation and anion is there, and this process will develop polarization. This is the phenomenon which is called as polarization, and this is the process which will develop covalent character. So this is the character of overlapping of orbitals. So due to this, they develop covalent character, and this phenomenon is called as polarization. So how this polarization can be explained? That is, when cation combines, so cation comes closer to the anion, then cation will attract the outermost electron cloud of anion, due to which their structure gets distorted, and finally cation and anion lies on the same region. This phenomenon is called as polarization. This phenomenon is called as polarization. Due to polarization, since cation and anion lies on the same region, which seems to develop some overlapping tendency, that is covalent character. Alright, and that is the reason Fajans over here states that, Fajans rule, Fajan states that, alright, 100% ionic compound does not exist in nature. 100% ionic compound does not exist in nature. 100% ionic compound does not exist in nature. Alright, does not exist in nature. In all ionic compound, there will be, in some cases, little polarization, in some cases, more polarization. So, in all the ionic compound, there will be some extent of polarization. Therefore, 100% ionic compound does not exist in nature. In all ionic compound, some value of their, some extent of their polarization, some extent of their covalent character. So, in ionic compound, some extent of their covalent character. Okay, that was Fajan's rule. Okay, again, according to this Fajan's, 100% ionic compound does not exist. In some of the cases, there is more value of their ionic, covalent character. In some of the cases, less value of ionic character. Suppose there is NaCl. Okay, there is NaCl. 100% ionic is not there. Some extent of polarization will be there. But if it is AgCl, their extent of polarization is more. So over here, polarization is less. Polarization is less. But over here, polarization is more. Polarization is more. That is why AgCl behaves as a covalent molecules. Behaves as a covalent molecules. As a covalent molecules. However, it is ionic, but they behaves as a covalent molecules. NaCl behaves as ionic compounds, ionic molecules, because their polarization is less. But AgCl, where polarization is more, they behaves as a covalent molecules. And therefore, NaCl is soluble in water, AgCl remains insoluble in water. Okay. Similarly, if there is lithium chloride behaves as covalent molecule. They remains insoluble in water, but soluble in organic solvent, like covalent molecules. So this is all about the polarization, alright, which will disturb their proper character, which will disturb their original character, alright, okay. Polarization depends upon many other factors. Polarization depends upon following factor. First is number of charge, whether it is cationic or anionic. Greater the number of charge, greater will be their polarization. Greater the number of charge, greater will be their polarization. Like suppose there is Na+, there is Mg2+, and there is Al3+. So obviously Na+ will have smaller charge, less number of charge than Mg2+ than Al3+. So obviously in this case, polarization increases in this order because number of cationic charge increases. So as the number of cationic charge increases, polarization increases. If you take F-, if you take O2-, if you take N3-, again number of charge increases, polarization increases. So in these cases, polarization increases because number of charge increases. So as the number of charge increases, polarization increases. As the number of charge increases, polarization increases. Okay. Now, second factor is, that is size of charges. Size of charges. Size of charges. Okay. What we can say? Cation will have polarizing power. So, polarizing power of cation. Polarizing power of cation is inversely proportional to the size of cation. Size of cation. Smaller cation, greater polarizing power. Bigger cation, lesser polarizing power. So, polarizing power of cation is inversely proportional to size of cation. As the size of cation increases, polarizing power decreases. That is the reason why, therefore, polarizing power decreases from top to bottom down the group. Top to bottom down the group. Polarizing power decreases from top to bottom down the group. That is, suppose we will take beryllium 2+, we will take magnesium 2+, we will take calcium 2+, strontium 2+, barium 2+, radium is radioactive in nature. So from top to bottom, what we can say? Their polarization decreases or polarizing power decreases. Polarizing power decreases. If polarizing power decreases, their covalent character decreases. Covalent character decreases. Covalent character decreases, but ionic character increases. Ionic character increases. Solubility in water increases. Melting and boiling point increases. Solubility in organic solvent increases. So all ionic character variation increases from top to bottom down the group, but their covalent character decreases from top to bottom down the group. And this is one of the reasons why basic character of metallic oxides or hydroxides increases from top to bottom down the group because of increase in their ionic character. Okay, because of increase in their ionic character. So this is another point, that is size of charges, that is polarizing power of cation. If you see the polarizability of an ion, polarizability of an ion increases with increase in size of an ion. Increases with increase in size of an ion, like F minus, Cl minus, Br minus, I minus. Polarizability increases. Polarizability increases. So covalent character increases. Covalent character increases. Ionic character decreases. And all variations we can explain. Alright. Third is, it was second one. Third is, that is types of solvent. Types of solvent. Again, polarization depends upon the solvent itself. Okay, because polarization takes place only in polar solvent. Polarization takes place only in polar solvent. Polarization takes place only in polar solvent, not in non-polar solvent. So polarization takes place only in polar solvent. Okay, not in non-polar solvent. So solvent must be polar to explain polarization. Next is types of electronic configuration. Types of electronic configuration. Which type of electronic configuration they will have? Generally we know that S block and P block. S block element will have less polarizing power than D block metal. Because D block will have unstable electronic configuration, therefore polarizes more. Like suppose there is NaCl and there is CuCl. So which is more ionic? NaCl is more ionic than CuCl. So this is the character of ionic. So ionic character of NaCl is more. Melting and boiling point of NaCl is more than CuCl. Okay, because copper is having more unstable electronic configuration. D block is having more unstable electronic configuration than S and P block, and therefore D block polarizes more than D block will have more polarizing power than S and P block. Okay, so if you see the polarizing power ability, so S block will have less than P block element, then D block element. So D block element will have high value of polarizing power, then P block, then S block element. Okay. Fifth is that is again nature of electronic configurations. It was types of electronic configuration. This is nature of electronic configurations. Like what does it mean? Nature of electronic configuration. Suppose by losing electron it becomes inert gas configuration. Then that particular ions will not have tendency to accept electron. They will have less polarizing power. Okay. So what does it mean? Like suppose there is Na plus. There is Mg2 plus. There is Cu2 plus. If we compare, in Na plus their configuration is 2s2, 2p6. In Mg2 plus their configuration is 2s2, 2p6. But in Cu2 plus their configuration is 4s0, 3d9. So these two acquires, alright, nearest inert gas configuration. These two acquires nearest inert gas configuration. Hence their polarizing power is less. And hence their polarizing power is less. But copper 2 plus does not acquire the configuration of inert gas, their polarizing power is more. Therefore, we can say if there is CuCl2 and there is MgCl2, MgCl2 is more ionic than CuCl2. This is ionic character variations. Ionic character. MgCl2 is more ionic than CuCl2, or CuCl2 is more covalent than MgCl2. Alright? CuCl2 is more covalent than MgCl2. If we take another example, that is Zn2 plus, they will have 4s0 3d10. 4s0 3d10. Now 4s0 3d10 is more stable than Cu2 plus. So then we can say ZnCl2 is more ionic than CuCl2. So ZnCl2 is more ionic than CuCl2. CuCl2 is more covalent than ZnCl2. Ionic character. Because 3d10 is configuration is stable configuration as compared to 3d9. Therefore, this will possess more ionic character, this will possess less ionic character. They will have less polarizing power than copper 2 plus. Okay, so that is nature of electronic configuration. It depends upon that also. So these are the factors upon which polarizing power depends on, polarizability depends, or simply we can say polarization depends. Okay, polarization has great role. Alright, because it will decide whether the molecule is having ionic character or molecule is having covalent character. Now, the variation of melting and boiling point we'll see. The variation of melting and boiling point, we have discussed this part in details, and everything is there in your notes. So please go through the notes. Variation of, just will revise, melting and boiling point of ionic compound. This depends upon many other factors. Two major factor is there: lattice energy and polarization. So lattice energy and polarization. So two factors are there: lattice energy and polarization. Lattice energy and polarization. So by using these two, we can frame two different cases. One is when lattice energy dominates. When lattice energy, dominates over polarization. Other cases, when polarization dominates over lattice energy. When polarization dominates over lattice energy. So when lattice energy dominates over polarization, one case, and when polarization dominates over lattice energy, that is another case. When lattice energy dominates, what we can say? When it dominates, lattice energy will be dominating if cation is bigger, anion is smaller. When cation is bigger, anion is smaller, alright, then lattice energy dominates. When polarization is negligible. So when polarization is negligible, when cation is bigger, when anion is smaller. When polarization dominates over lattice energy, when cation is smaller and anion is bigger. When cation is smaller and anion is bigger, then polarization dominates. And when polarization dominates, their melting and boiling point decreases. When lattice energy dominates, melting and boiling point increases. So when this is the case, this case will increase melting and boiling point. Melting point and boiling point increases over here. In this case, melting point and boiling point decreases in this case. So decreases over here. Melting point, boiling point increases, melting point, boiling point decreases. Like for example, okay, suppose we have Na2O, okay, then K2O, then Rb2O, then CS2O, alright, all this. We have NAF, we have KF, RBF, CSF, etc., etc. This series. So what we can say, in this case, all are having this cation and anion, cation, anion, cation, anion, cation, anion. So lattice energy decreases, lattice energy trends will be Na2O will have higher value of lattice energy, then K2O, then Rb2O, then CS2O. See, Na plus will not have polarizing power, much polarizing power. It cannot polarize the electron cloud of oxide ions. It cannot polarize the electron cloud of oxide ions. Therefore, melting point variation will be this, same. So, melting point variation will be same. Same will be there. Melting point variation, boiling point variations as that of this lattice energy. If you see the NAF, so lattice energy trends of NAF will be again, NAF will be greater than KF, KF will be greater than RBF, RBF will be greater than CSF. Okay, then melting point order will be same. So melting point order we can say same, that is NAF will have higher than KF, then RBF, then CSF. Now, in this case the product of charge is more. Na2 plus, that is Na plus and O2 minus, 1 into 2 to 1 into 2 to, product of charge remains same. The variation is of size only, and as the size increases, lattice energy decreases, melting and boiling point decreases. Over here, there is Na plus and F minus, product of charge is less, that is 1. 1 into 1, 1 into 1, all those. So, product of charge is less. If we compare these two, which will have higher melting point, obviously Na2 will have higher melting point than NAF. Why? Because product of charge in this case is more and product of charge in this case is less. Okay. So, like that we can calculate, we can explain melting point variation and boiling point variations in ionic compounds. We have discussed about this and details that is there in your class notes. So please go through that class notes and once again you go through the variation of their melting and boiling point, whichever the trends you have written. Okay, go through that. If you will have queries, then you should ask your queries by sending your doubts. Okay. Then we'll go for, just because we are doing revision itself, we cannot go for all those because it will take much time to do that. Okay, as you have seen in classroom itself, classroom discussion, it took much time to discuss all those. Variation of solubilities. Again, the solubility variations can be explained by using two factors. Basically, one is lattice energy trends and other is polarization. So, one case will do, case 1, when polarization is dominating. When polarization is dominant or dominating. When polarization is dominating, lattice energy doesn't have any role. Polarization is dominating, what we can say? In this case, lattice energy is ignored for them. Like, suppose there is AgCl, AgBr, AgI. So, what we can say? Their covalent character increases. Polarization increases, covalent character increases, therefore their covalent character increases, solubility in water decreases, solubility in organic solvent increases. Similarly, if you see NaCl, NaBr, NaI. So again we can say relatively polarization increases, covalent character increases, solubility in water decreases. Okay. Similarly, we will take PbCl2, PbBr2, PbI2, Same trends we can explain. We can say ZnCl2, ZnBr2, ZnI2. Same case we can explain. We can take HgCl2, HgBr2, HgI2. Same case we can explain. So in all these cases, polarization is dominating factors. So when polarization is dominant, then lattice energy has no role to explain their solubilities, and their solubility in water decreases with increase in polarization. Okay, solubility in water decreases with increase in polarization. Next case is what? That is when case 2. When lattice energy is dominating. Lattice energy is dominating. When lattice energy is dominating, then how it can be explained? Let's say we have NaCl. We have added in water. This becomes Na plus Cl minus. Now it is aqueous. Okay. So how it happened? NaCl is converted to Na plus Cl minus. This is gaseous. Energy involved is ionization or lattice. Enthalpy of lattice for this compound. Now this is Na plus is added in water. Cl minus is added in water. So over here hydration enthalpy is there. Hydration. Over here hydration enthalpy is the energy change. This hydration enthalpy will be negative. This value is positive. This solution dissolved, that is enthalpy of solution is there. Okay. This is the net process which is involved. Enthalpy of solution. Okay. Then enthalpy of solution is equals to enthalpy of ionization plus enthalpy of hydration. This is equals to enthalpy of ionization, alright, that is K 1 by R of cation plus R of anion plus K2 by R cation plus K3 by R anion. Okay, this is the value of this. If hydration enthalpy which is negative, so hydration enthalpy is negative, so this we can explain. This value is negative, this value is positive. So if enthalpy of ionization is greater than enthalpy of hydration, what we can say, alright, molecule remains insoluble. Molecule remains insoluble. If ionization enthalpy is more than enthalpy of hydration, then molecule remains insoluble. If ionization enthalpy is less than enthalpy of hydration, then molecule will be soluble. Molecule will be soluble in water. So it will be soluble in water. Okay. Again, this we have discussed in details. For the solubility delta Gs, solution is delta Hs plus minus T of delta Ss. Okay, this is for gives energy for solution. This is enthalpy for solution. This is entropy change for solution. Okay, when we dissolve, while dissolving, while dissolving, while dissolution, what we can say, delta HS can be positive, can be negative, positive or negative. Delta SS, that is entropy, it is always positive because entropy always increases while dissolving because number of ions increases. So delta SS is always positive. And for the dissolution, delta GS must be negative. Okay, how we can explain? So through this we can explain different case. Case 1. If delta HS is negative, that is what? Exothermic dissolution. If there is exothermic dissolution, delta SS is always positive. So what we can say, delta GS is equals to minus of del HS minus T del SS. Okay. If this is negative, what does it mean? Dissolution is always negative. Dissolution, alright, takes place with decrease in free energy, with negative value of negative del GS. So that is what? Molecule is soluble. So if del HS is negative, molecule always remains soluble. Okay, that is the case 1. Case 2. Why soluble? Because del GS is always negative. Case 2. If del HS is positive, then there are two different cases. What we want? We want del GS negative. Del GS will be negative. Okay, how it is? We have two different cases. We will explain these two different cases over here. So again, first case is when del HS is positive, okay, del GS is equals to del HS minus T del SS. This is to be negative, but this is positive. What to do? How this value will be negative? When this value is greater than this value. So when mode of T del S is greater than del H, then del GS is negative. Then del GS is negative and molecule is soluble. Okay, the dissolution is possible. So how this can be achieved? By increasing temperature. So either this can be done either at high temperature, okay, either at high temperature or by large increase in entropy. Therefore, there are some molecules which remains insoluble in cold water but soluble in hot water. Because at hot water, at high temperature, this mode is greater than this mode, and therefore del GS is negative and process is possible. Okay. Again, in some cases what happens, there is large increase in entropy, and large increase in entropy again will increase this mode than this, and again their del GS is negative. So this is the case of solubility, alright, in ionic compounds. If we explain the variations of ionic compound can be explained like this. Del HS is equals to K1 by RC plus RA, we have seen, plus K2 by RC plus K3 by RA. By using this relation, we can explain, and we can say if there is, like suppose there is different cases when cation is much smaller than anion, when anion is bigger than cation, when anion is smaller than anion, cation, or comparable to cation. Like that, different cases we may observe over here, and all those cases we have seen, we have given their explanation, alright, in your class notes itself. One case is when there is smaller anion. In case of smaller anion, alright, with increase in size of cation, their enthalpy of dissolution decreases. Okay, their enthalpy of dissolution decreases. In case of smaller anion, what we can say, if smaller anion is there, their hydration enthalpy will be more than that of their lattice enthalpy, and molecule becomes soluble, their solubility increases. If there is bigger anion, in case of bigger anion, their enthalpy, decrease in their lattice energy is less than that of decrease in hydration enthalpy. So, decrease in lattice enthalpy is greater than that of decrease in hydration enthalpy, and therefore, lattice enthalpy value will dominate over their hydration enthalpy and molecule becomes insoluble. That was the case, and different cases we have observed in this case. Please go through the notes, you will get everything over there. This is about variation of their solubility, variation of melting and boiling point, ionic bond, alright, characters of ionic bond, polarization and all. Okay. Now, we will go for covalent bond. We will go for covalent bond. Covalent bond is the bond which is being formed by the mutual sharing. Formed by mutual sharing. Formed by mutual sharing of electrons. It is formed by mutual sharing of electrons. When there is mutual sharing of electrons, alright, in between similar or dissimilar atom. In between similar or dissimilar atom. Okay, having electronegative difference less than 1.7 or 0. So, this covalent bond is of two types. One is called as non-polar covalent bond, other is called as polar covalent bond. Non-polar covalent bond, that is electronegativity difference is equals to 0. Polar covalent bond, electronegative difference is not equals to 0. Polar covalent bond, electronegative difference is not equals to 0, and non-polar difference is 0. Like, for example, there is O2, N2, Cl2, Br2, okay, etc. Simply, alright, S8, O3, can we say that, etc. So, electronegative difference between two or more atoms is equals to 0, then they will form non-polar covalent bond. If it is polar covalent bond like HCl, HBr, Hi, NH3, H2O, and simply we can say etc. Many such examples are there of polar covalent bond. Polar covalent bond. This polar covalent bond and non-polar covalent bond. Non-polar covalent bond will have, alright, non-polar covalent bond, they will have partial, attractions among the molecules. Polar covalent bond may attracted through stronger bond, no problem. Covalent compounds are possessing lower melting and boiling points because covalent forces are weaker force. So, strongest is ionic force. Strongest is ionic force. Ionic force is weaker than covalent force. Ionic force is weaker than covalent force. Okay. So, ionic bond is stronger than covalent bond. So, therefore, covalent molecules possess low melting and boiling point. Ionic bonded molecules possess high melting and boiling point. Covalent bond is non-polar and directional in nature. Ionic bond is polar and non-directional in nature. Ionic compound dissolves in water. Covalent compound remains insoluble in water but soluble in organic solvent. Alright, many other factors can be explained about this. Okay. Now, this covalent bond which is divided into non-polar and polar, now it can be explained like suppose there is hydrogen, oxygen, hydrogen. So, this bond is polar. This bond is polar. So the bond is polar, therefore H2O molecule is called as polar molecule. Such molecule is called as polar molecule. Okay. This compounds, covalent compounds can be divided into different category. One is, that is electron deficient compounds. One is electron deficient compounds. Other is electron precise compounds. Other is electron rich compounds. Electron rich compounds. Okay. Covalent compounds can be electron deficient, can be electron precise, can be electron rich compounds. Alright. It can also be divided as supraoctet molecules. Supraoctet molecules. Supraoctet molecules. Molecules which is having more than 8 electrons in their outermost shell. Supraoctet molecule means molecules containing more than 8 electrons, in their outermost shell. Containing more than 8 electrons in their outermost shell, that is supraoctet molecule. Electron deficient molecules like BF3, BH3, AlCl3, alright, etc. BCl2, etc. They are electron deficient molecules. They are having less than 8 electrons in their outermost shell, so they are electron deficient. Boron is having 3 electron of fluorine, alright, after sharing. So boron will have total 6 electrons in their outermost shell, again 2 short of 8. So that is electron deficient molecules. Now electron precise molecules, like suppose CH4, SiH4, alright, SiH4, etc., GH4. So they are electron precise molecules. Electron rich molecules, like suppose NH3, H2O, HF, alright, PH3, H2S, can we say that, etc. That is, they are having electron pair in excess. That is called as electron rich species. But supraoctet molecules, that is having more than 8 electrons in their outermost shell. If it is more than 8 electrons in their outermost shell, examples of such molecules are like SF4, SF6, PCl5, IF7, ClF3, etc. we can say. Sulfur is having 6 valence electron, 4 is overlapped with fluorine, so 6 plus 4, 10 electron in their outermost shell, 6 plus 6, 12 electron in their outermost shell, 5 plus 5, 10 electron in their outermost shell, and 7 plus 7, 14 electron, 7 plus 3, 10 electron. So all are having more than 8 electrons in their outermost shell. They will be called as supraoctet molecules. Okay, so these are the characteristics of some covalent compounds. Okay, then in next class we will go for dipole moment variations, which again important properties of covalent compounds. Okay, so in next class we will discuss about dipole moment. I hope, alright, you are able to revise your class notes properly. Alright, after seeing this video. Okay, thank you very much. Thank you.